All right, so the
All
floor
right,
is yours, Mark.
thank you very much. Everyone can hear me and see the slides?
Yep.
Great. All right, so I'm a postdoc in the database architecture group in CWI. Before that, I was a PhD student there, and before that, I was a master student there. So in summary of me, I like the CWI and I like databases. That's kind of most of what you need to know about me. So in our group, we work on relational database management systems, or RDBMS for short. You may hear me saying database when I mean RDBMS. This is a common misconception. Database means just the data set, but I may interleave them. I always mean RDBMS. So database systems, of course, they're very popular. Many of you have probably used or been introduced to database systems at some point. They are taught in computer science curriculums. You learn SQL and such. They're basically used everywhere. They hold most of the important data in the world. But they have been around for a really long time. So basically forever in computer science terms, which in real terms, of course, not that long. They kind of date back to 1970 when Edgar Codd presented a paper, a relational model of data for large shared data banks. And this kind of kicked off the way of modeling data as these sort of separate tables and or relations. It's the same thing, table relation. After that, in 1974, we had the paper called SQL, a structured query language, which was a description of the language used to retrieve information from these databases. And the language is, for those not familiar, it kind of mimics English, or it's meant to mimic English. So it's usable by people that are also not actually programmers themselves. And that's kind of it, you know. So since 1974, very little has changed about that. So SQL, the relational model, they are still ubiquitous. They're still used everywhere. So you might be wondering, well, that's almost 50 years ago. What the hell have all you database researchers been doing this past like half a century? Why are we even paying you, you know? Well, one very nice thing about SQL, about the language, is that it's declarative, which means that the user describes what they want to see. It doesn't describe exactly what the system has to do to get the data. And that's a very important distinction from a traditional programming language in which you tell the computer step by step what to do. And because it's declarative, the database system itself can kind of decide the best way of answering specific queries, or the best way of retrieving the data. And that gives the system a lot of freedom in how it's implemented and how it's done. So while the front end, while SQL might not have changed, the systems under the hood have certainly changed immensely in the past 50 years. So that's basically what the database community has been working on, optimizing these systems, making them faster, making them more efficient, making them consume less disk space, less memory. So the original systems, they were very simple. They were made for, well, simple, they were not very simple. They were made for simpler scenarios, for low data sets, small amounts of data, because they also had to run on computers that had just kilobytes of memory and maybe megabytes of disk space. And the modern systems, they are again completely different because they're optimized for computers that actually have maybe even terabytes of memory, or they even run on clusters of computers with many computers connected together to work together to answer individual queries. So, well, data has been important for a very long time. Of course, I mean, data is, it's kind of central to most applications, to most computer programs. But the past 10 years, it's been getting kind of increasingly hyped or popular. Of course, you first had like this whole big data thing like 10 years ago. Now you have machine learning, which is also basically completely centered around data. And the main reason for that increase in popularity is that storing and analyzing data is incredibly cheap now. Whereas if you go back like 20, 30 years, storing like even a few customers or like names would cost you hundreds of thousands of dollars. Now you can store gigabytes, even terabytes of data on like commodity laptops and desktops. So basically everybody can afford to store any data or most data sets they want, and everybody can afford to analyze this data as well, which is what we're seeing with like even like small companies working on analyzing data and such. So there's been a huge push here. And the new trend, kind of the overarching term, is called data science. It's a very overloaded term. It can mean a lot of different things. If you Google it, you get this nice Venn diagram. And you can see here, they say it's a combination of computer science, of math and statistics, and domain/business knowledge. It's pretty accurate. For me, I like to see it as just statistics on a MacBook, which I think is a pretty apt summary. It's very correlated related to statistics, of course, about gathering like chances, percentages, and such. I got an animation there. So data scientists, they work with data. And our field, we've been basically spending half a century perfecting data management systems, right? So you might come to the logical conclusion, obviously data scientists use database management systems, right? Well, no, unfortunately not. They tend not to use them. They use them only if they're absolutely forced to use them, mainly if the data they want to analyze is already stored in a database system. And otherwise, they kind of prefer to avoid using database management systems. And as you can see, that makes our database system very sad, and makes me personally very sad, of course, as well, as a database researcher. I want people to use our stuff. So here's a nice quote from Hadley Wickham. If your data fits in memory, there is no advantage to putting it in a database. It will only be slower and more frustrating. Ouch, it's a pretty heavy quote, right? It is essentially calling our systems slow and frustrating. And Hadley Wickham, for those that don't know him, he's kind of like the lead R guy. He made like all of R's most popular packages. He works on RStudio. He made ggplot. He's basically the R guy, which is one of the main tools used for data science. So he's like a really big figure there. And he has this to say about R systems, you know, so that hurts. So maybe the conclusion is that they just don't need that technology, right? And of course, if they don't need the technology, then why would they use it? So let's look at what data scientists actually use. Well, if we look at the most popular Python packages used by data scientists, we can see the top two are NumPy and Pandas, which are data wrangling libraries. Then we have Matplotlib, which is a plotting library for making shiny graphs, basically. And then we have a whole bunch of analysis, classification, and ML libraries like SciPy, TensorFlow, and such. I assume you've probably heard some of these names come by if you're not even using them yourself. So these are kind of like the top packages. In R land, things are not much different. So if we look at the most downloaded R packages, we can see the top two, they are Rlang and RCPP. So these are kind of like not really relevant here because they are dependency packages. They're used by the developers of the packages, but they're not actually used by the end user. The packages that are used by the end user are dplyr and Tibble and data table, which again are data wrangling libraries. Then you also have ggplot, which is a plotting library. These are the kind of the most popular things. And always at the top is the data wrangling, basically. That's the point. And what do all these data wrangling libraries have in common? Well, they perform database operations. You know, they perform joins, they perform aggregates, they perform basic data transformations, filters, updates, deletes. So basically, these data wrangling libraries, they're kind of implementing a poor man's database, if you will. So data scientists, they clearly do need the functionality that database systems offer. So let's go back to Hadley's quote. He calls our systems slow and frustrating. Why does he think that? I mean, frustrating maybe, but slow. We've been working on optimizing them for half a century. What's going on there? You know, like, are we just all like not good at our jobs or so? Like, well, to maybe answer that a bit better, let's run a data science workflow, both with and without a database system, and see what happens. So I have made a very small example data science workflow. What they typically look like, this is a kind of a simplification, of course, is that you load your data from somewhere, often CSV file. You perform some data cleaning, pre-processing. We often call this ETL, extract, transform, load. And then we run our analysis. So for our little example, we have some voter data from all the people that voted in North Carolina. They very, very nicely make all of this publicly available for anyone to download. It's about 360 megabytes in CSV format. Then as a pre-processing step, of course, we're going to load this file into Python. and then we're going to, into R actually, and then we're going to remove entries that have a missing phone number or house number. Then, so basically for any person where we don't know their house number or we don't know their phone number, we're going to remove them. And then we're going to see if there's a correlation between someone's phone number and someone's house number. Prediction, probably not, but let's see. So in pure R, so without a database, what we would do is we would first install the required packages if we don't have them already, right? It's our first time. We would just do install packages, data table, dplyr. Nice, that works. Then we run our analysis. We first load the data from the CSV file. We can use this function fread, pass the CSV file. Then we filter entries that don't have a phone or house number. So you can see this is_na being used there, is not a number, is not existent. We filter all the answers that don't have a phone or house number. And then we perform the correlation. And this is just done through this core function, COR in R. And you can see, well, minus 0.002, it's not a strong correlation. So it's basically random. There's no actual correlation between a phone number and a house number. Surprise. But let's now do it with a database server. It's with Postgres, which is kind of one of the most popular open source database systems used. First, what we have to do is install the database server. And of course, it's all run on our Silence cluster and where we don't have roots. So that makes it even more fun because it's not actually so trivial to install these things without a package manager. We have to download the sources and compile them. Fine, I skipped those steps here. If you have a package manager, it's easier. Then we have to launch and set up the database server. The way to do that with Postgres is you first create this environment variable, PG data, which you point towards where you want the database to live. Very, very clean, of course, using environment variables for this, perfect. Then you call initDB, which sets up the database server, and then you call pgctl, which is short for Postgres control. But because this was made a long time ago, they had to save on the characters there because it was very crucial to the storage, you know. So you set up the database, you start the log file, and then we have a running database server. Then we have to install the client because it's a client server setup. And this we can do through R's package management system. We can do install packages, R Postgres. Except it didn't work. If you look at this error, well, I don't expect you to read that. Basically, it's complaining it can't find the server of Postgres, which is a bit strange because we want to install the client. But apparently, to install the server, you need the client in the path. And because we didn't use a package manager, it's not the path. Okay, fine. We fix our path, we set up some more environment variables, install it again, and it works. Then we can use it. So now we have a running database server. We have the client installed. This was already quite a headache to get here. Now we can use it. First, we connect to the server. We use this DBI here. And then because it's SQL, we have to create a table. We have to create a schema. And you see here, I run this create table command, create table NC voters. And if you look, you see there's 3 dots there, dot, dot, dot. I'm being very generous here. This table has 100 columns. It's not very nice, the schema definition. It would not even fit on this slide, basically. So I'm already kind of simplifying it. Then we're going to load the CSV file. We do that using a copy statement. And you can see here, I use this paste 0 command, which is basically string concatenation because we have to get our current working directory in there. It's also not so nice, you know, to use string concatenation to combine these things. It's not very clean. But all right, so we do that. Then we filter out using a delete. We filter all the entries that don't have a phone number or house number. Then we do a DB read table, which loads the data from the server into the R client. And then we can again use our correlation function. And then after that, we get the same result, but time-wise not. If you look at this result, Postgres using the database server, it's significantly slower. It's like a factor 3 slower than just using R. And you might be wondering why it's a database server. Well, if you look at the code, the magic thing that happens there is this DB read table. And this basically pushes this entire table from the database server to the client. And this is a huge overhead that all sends over a socket connection. But it's also a necessary overhead because we have to get the data from the database server into the client somehow to be able to use our R functions, right? And that's basically what causes this huge performance degradation. So if we look at this, Hadley is right. For these types of workflows, database systems, they are frustrating and they are slow. What are the problems and how can we fix them? Because we would like them to use our systems. Well, the problems we've seen so far, it's difficult to install, difficult to set up and maintain. There's a slow data transfer to and from the client. We have a poor interface, which requires us to use the string concatenation. And we have external state, right? Which we have a server running in the background. And that's kind of crucial because it means we can't copy paste code around. I will get back to that a bit later. So standard database systems, they always run with this client server architecture. And it's great if you have multiple users or you run your database server on a separate machine. But with these data science workflows, that's usually not what's happening. And then this architecture, it's kind of pointless. It just makes everything more cumbersome, more difficult, right? Having to maintain the server, launch the server. We've also seen that for these workflows, the installation, it really has to be easy. You can't ask someone to like download sources from the internet. They have to use their native package manager. So you have to be able to do like pip install or install packages because otherwise it just adds too much complexity to use the system. We've all seen transfer efficiency. It's very crucial because SQL is not sufficient for all data science. You know, you can't easily run like an ML model or like some classification inside the database, inside SQL. So you have to, at some point, put the data into your R Python process, which means you have to transfer it. But these connectors, they're not built for this bulk transfer. We had a paper on this before. We had to work on this, on optimizing the connectors. However, even with like our optimized implementation, there's still a lot of overhead there, of course, of the actual socket. Then also SQL, I think it's a very nice language, but as an interface for clients, it has some problems because embedding these strings, it's kind of unnatural. It's kind of a hacky solution, right? You have to use the string concatenation. You get no syntax highlighting usually, which is kind of ugly. It doesn't really like fit into your IDE very well. And basically it's so hacky that there's like a whole class of security vulnerabilities dedicated just to this embedding. You know, like SQL injection exists only because we do this interface, this kind of weird embedding. Also, another problem is that SQL as a string, it's not so easily composable. So in dplyr, which is like an R data wrangling library, we can chain operations. We can do first, we get the table, then we apply a filter, then we do a selection. And that also, that chaining of individual operations means we can easily say at any point, like if we want to inspect it, we can say like, okay, show me this like partial result. And that's really useful for data debugging. Like if you want to know, like maybe this filter removed all of the rows because you had a mistake there, a bug there. If you just have like a complex SQL command, it's difficult to look at all the intermediates and see where it went wrong. But here you can see it's very composable. You can look at the intermediates. You can kind of do it in SQL with temporary tables, but it's a lot more cumbersome and you have to write a lot of stuff manually. Whereas with this composable interface, it's much more natural. Yeah, so the cannot copy paste thing is also kind of crucial for the learning process because often people, especially like if you're beginning to do these data science workflows, you'll find some code from the internet that you just want to run. And in R Python, it's interpreted. The nice thing is usually you can just copy paste it in your terminal, right? But not if the code relies on an external state like a database server. So if we have this dplyr code, we can just copy paste this. But a code that relies on a database server running, you can't. And that's kind of, it complicates things quite significantly for the user, especially for novices, for people that are just getting started. So basically what we've seen is that the current systems, they're not a good fit for data science. Well, why do database researchers even care? Obviously the answer is money. Data science, it's popular, so you can get grants, you can get money, great stuff. But maybe more of like a fundamental reason is that data scientists, they are kind of reinventing database systems. They're doing a lot of the same things that we have already done like 30, 40, 50 years ago, you know? And they are kind of remaking all the mistakes that have been made in our community as well. And it's kind of a waste. So if you look at these systems they've made, they're kind of like a poor database system. From our perspective, they have no optimizers. They materialize huge intermediates in memory or on disk. They don't have out of memory computation. They don't have parallelism. They don't do like compression, compressed execution, don't have scalability. They're kind of a very poor database system. And that, of course, makes us sad because all these problems database systems can already solve and more as well, like data integrity and such. It's all things that database systems have been engineered for. And while current database systems are slow and frustrating, they don't need to be, right? Like it's not a rule that says that this has to be the case. And that's kind of why we started working on DuckDB, an embeddable analytical database system. We wanted to create a database system that's actually nice to use, like not one that you bash your head into, but one you actually enjoy to use, basically. Well, the first question we always get is why DuckDB? Well, Hannes, my co-worker on this, he used to own a pet duck. So here's a picture. The name of the duck is Wilbur. So in homage to the duck, we named the database DuckDB. So DuckDB, as the title says, it's the SQLite for analytics. I don't have a slide explaining SQLite. SQLite is another database system that is known to be really easy to use, but it's not catered towards like big data set. It's really made for like smaller data sets, like megabytes of data and such. So it's not a good fit for these workflows, but we learned a lot of lessons from them on how to be easy to use, basically. So the core features of DuckDB is that it has a simple installation. It's embedded, so there's no external server management. You can just copy paste these Python code snippets. It has a single file storage format, which is also kind of crucial. A lot of databases use like directories and such, but users kind of like single files. We have fast analytical processing and a fast data transfer between our Python and database system. So simple installation and uses. Like I said, here we learned a lot of lessons from SQLite. It's embedded. We don't have any external dependencies, so you don't have to worry about like linking or compiling other libraries on your system. We have an amalgamation, which means that our whole system can be like put into two single source files, just like duckdb.cpp, duckdb.hp, which is all you need to install it. Makes it a lot easier to integrate into your build toolchain. And it's integrated into package managers. So you can just run like pip install duckdb, install package duckdb, without having to like download source files yourself and compile them and deal with all this mess, basically. Also, no external state, no like magic environment variables or config files in your home directory that are needed to function, and single file storage, because it's much easier for users typically. It introduces some technical difficulties for us as engineers, but for users it's a lot more easy to handle, because they can just like drag one file into their email even, or like SCP1 file. You don't need to worry about like directories. We also have a composable interface. So while we do support full SQL as well, we also have this relational API, we call it, where you can like compose individual operators. So here's an example of using it. You can call, say like duckdb.open and then open a database file. Then on that database, you can get a table, you can filter that table, and you can perform aggregates. And you can perform joins as well. You can perform basically anything you can do in SQL. And the nice thing is, because of this like individual steps, you have like dot table, dot filter, dot aggregate. You have also full composability, and you can again inspect these intermediates. So here you can see we store this like filtered data set in a variable, and then we can do dot show, and it will print us the intermediate. And this allows us to have like this composability. Another nice thing is that we have very tight integration with native structures. So if you have, for example, Pandas data frame, we can directly operate on that Pandas data frame. And this is also a nice thing about being embedded, because we run in the same process. We can just read that data frame without having to transfer any data, right? It's basically free for us to read it. And one nice side effect of that is that we can even run like SQL on Pandas data frames, because it can just the Pandas data frame can just go through our engine as if it was a table of in our system. We also support efficient ETL workloads, a bit more databasey. So traditional systems, when it comes to updates, deletes, columns being added or removed, they're not really optimized for the cases where you want to do that for like big values, whereas with like a lot of values, a lot of rows. So normally, if you would have a traditional database system, it would be optimized for, say, like changing one row out of a billion. But in these ETL workloads, you're usually altering like whole columns, or adding a whole new column, or deleting like half your data. And they are just not optimized for that. So DuckDB, it's the opposite. We have optimized it specifically for that. So if you have a query, for example, this query where you replace a magic value with like a proper null, which is quite common in certain data sets, it can update the whole column, and DuckDB is optimized for this scenario. We also have efficient snapshotting. So typically, if you run an ETL pipeline, it's like load pipeline in Python, you're kind of like doing a trial and error thing because you don't know the data yet. And anytime you make a mistake, you usually have to start over, which involves reloading the CSV file, rerunning a bunch of operations. And if you work with a big data set, it can take a long time. So it's kind of annoying. So in DuckDB, we have versioning of data that can be used here. So you can have like different versions of the data. And if you try something new and it doesn't work, like for example, by accident, you delete like your whole database instead of just the rows that you want to delete, you don't need to go back to the beginning. You can just do like a rollback and we'll efficiently revert back to a previous version using MVCC. It's a concurrency control mechanism. It's a database form. So DuckDB, free and open source. Of course, we are working on it. It's currently pre-release mode. So we started working on this, I think, almost 2 years ago at this point. But it's still kind of like in a beta stage, let's say. But feel free to use it. We have a website, duckdb.org. We have the source code online on GitHub. So yeah, if you're interested, if this at all resonated with you, then please try it and send us a bug report if you break anything by accident. Thank you for your attention and happy to take any questions.
Thanks, Mark. I think actually I was the target audience of your talk.
Really?
But let's see. Let's see. We have some questions. I think the first question is from Adrian. He says, very nice. Can I also put custom types objects from Python in the DB?
So
or put an ORM.
So we don't have this yet, but it is something we have actually thought about quite a lot. We have worked on adding arrays and such, but directly putting Python objects we don't have yet. But it's something we did actually want to add. So if you are interested in this, then please open an issue on the GitHub, because we are, we were also taking feature requests if you have like a good use case for this. So.
All right. And there's another question from Thijs Veugen. What if you compare DuckDB to a typical data science algorithm? I'm not sure what the
maybe a typical data
question is,
maybe
maybe you understand.
Wrangling algorithm is what you mean, like comparing it to say Pandas. So.
He talks about efficiency.
Oh, okay. Well, the thing is that if you look at say Pandas or so, what happens is in Pandas, it's every operation you do, it will be fully materialized in memory. It's all single threaded, and there's no optimization going on. So if I go back to, let's see here, for example, to go back here, you can see what we're doing here is we are only using 2 columns, right? You can see we're only using the phone number and the house number. That's all we're interested in. However, in Pandas and dplyr and such, they will always do everything on the whole table. And that's if you have a lot of columns, it can slow down things by really significant amounts. So if you have say 100 columns, you only insert in 5 of them, but you do like filters, projections on the whole table, you are writing like tons of data for no reason. So like really the performance gains are in essence limitless. It really depends on your workloads. We are doing a lot of optimizations there that allow us to skip work that is not possible or not done in like typical Pandas settings, basically. So it's for like, it really depends on the workload, basically. It can be low, the performance gain, but can be really high as well.
All right, I have a short question myself. So have you also considered maybe being some sort of backend that could, for example, be used inside Pandas so that for users, they wouldn't have to sort of worry about which tool they use?
Yeah, so this is something that's also has some traction in our community, but this is mostly a game of politics as well. So Pandas, in some sense, has one big advantage over the way we are doing, which is that it does everything immediately when you ask it to do. And that really limits optimization opportunities. But if you have like an error in it, then the error gets thrown immediately. Like, so suppose that you have like a division by 0 or something, right? You will get immediately the error when you run it. Whereas in the method we are doing, it will only happen when you actually execute the data. So there are like some advantages to doing it the way Pandas is doing from a usability perspective. And like just from a political perspective, of course, if you want to change the internals of pandas, it's used by so many people. It has to be one-to-one exactly compatible with what it's doing right now. And that is often also that forces kind of insecurity or like unoptimal code. It forces you to be inefficient in a lot of ways because you're forced to stick to the interface that they designed that was not designed for optimization, basically. So it's a nice idea, but politically not very feasible because of like all this reliance on the exact behavior that pandas exhibits right now.
Yeah, yeah, I see. All right, I think with that, let's officially end the scientific meeting now. So let's thank our speakers. We can do it
hold on.
in the chat.
Janice, I have one question for.
Oh, sure, yeah.
So Mark, thank you so much for this nice sales pitch, and I'm very curious to try it out actually. But one first question would come is that if you're trying to replace or present a new technology, have you talked to actual data scientists about their current workflows, and have you introduced DuckDB to their workflows and seen from their perception how it's actually being used, rather than just getting feature requests through?
So we have talked to some data scientists and seen it a bit, but not really to like a super big extent. And it's something we are actually very interested in. So if anyone here at the CWI as well is interested in using this, we would be super interested in working with you as well and seeing like the problems you encounter and if we can fix them and such, because we have done it a bit, but it's super valuable for us, especially in this stage, to like get this feedback as well, of course. So.
Cool, thank you very much. So
thanks. It's excellent point, Abdallah. Thanks for making that. So let's officially close the session now. So if you want to thank our speakers, you can do it in chat. And then I would invite maybe those with questions to maybe post their questions now. For example, for Sophia, we didn't have much time to answer questions. But the meeting is now officially over. So if you want to leave, please feel free to leave. So thanks.
Thank you, everyone.
Thank you.
Yeah, there were nice talks indeed, and it's really a pity that we didn't see a higher participant count this time. But
I think it has something to do with the weather also.
Very convinced, but maybe that's my delusion.
It's something like 30 degrees right now, right?
Yeah, it's very warm, so it's very.
Which is also too hot for some people, perhaps. I don't know.
I can understand.
Yeah, but the talks have been recorded, so I will soon stop recording and then hopefully process the videos, and then I'll share them also with you, Sophia and Mark. Then you can have a look whether you want them to be posted.
For me, it's
can,
perfectly fine to post it. I already, I know. I think I didn't say anything stupid, so I'm perfectly happy with them.
There's some questions from Adrian, and Adrian, feel free to ask them directly if you want. I think it's no problem.
Yeah, maybe it's much easier if I'm asking in person. Let's see. Yeah, so my first question was, I'm kind of interested from the CT perspective, if we can use this database as well, just thinking out loud. And I was wondering if we have a lot of big data, does the database need to be run fully in memory? Because that would be a problem to us because we easily run out.
It does not. So it's actually something that we are still working on expanding as well, but you don't need to load everything in RAM. Like you can set a memory limit on your database system, and then basically it will cache what it can in RAM based on that memory limit. You don't even need to set it to like all of your RAM. You can say like, here's like 4 gigs, you know, and then it will read from disk what when it's like needs to, basically. But it's something that's depending on your workload. There are some queries that don't quite work nicely with this, especially if you have joins. But for like typical aggregations and such, it works quite well.
Okay.
So try that, but it's in progress.
Okay. Oh, that's good to know. So, and then I think in SQLite, you would have like one big file that contains the whole database, right?
Yeah.
And then with DuckDB, would you have the same setup, or can you also say pull the big files or the blobs, pull them out and store them somewhere else?
Well, you could always store links to blobs in a file. I think that's kind of maybe standards in a database system, right? Is that you can just say like, okay, I store images, but I don't actually store the images. I store like a string with a path to a string with the image.
Right.
That you can of course do always.
Yeah.
In general, if you just put everything in the system, it will all be in one file. Yeah, that's kind of the current setup.
Yeah. Okay. So that makes a lot of sense. Okay. Thank you.
No worries.
Sophia,